Hi everyone, my name is Steve. Today we're going to talk about another very famous sorting algorithm called quicksort. It's actually the built-in default sorting algorithm for a lot of languages because it's super efficient on average. Now let's dive into more details about quicksort. So we'll first analyze how quicksort is usually implemented. Later on, we'll dive into the real code, how we can implement that. Then we'll briefly talk about its time and space complexity. Alright, now let's dive in. Alright, now let's get started. Quicksort. Quicksort has a worst-case time complexity of O(n) squared. Despite this very slow worst-case running time, if you recall, only insertion sort has this worst-case time complexity. Both heap sort and merge sort, their worst-case time complexity is only nlogn, which is way much better than O(n) squared. Despite this very slow worst-case running time, quicksort is actually the best practical choice for sorting because it is remarkably efficient on the average, which is O(n)logn. And another great feature that quicksort usually brings is its in-place sorting. The space complexity is O(logn), it's not O(1). So you may wonder, if it's in-place sorting, just like insertion sort, then why the space complexity is not O(1) constant time? For now, just keep this in mind and we'll discuss why after we walk through how quicksort really works and how we finish up coding in real Java code. Then everything will make sense. The strategy that quicksort employs is very simple to merge sort, which is divide, conquer, and combine. Let's see, the first step is divide. It will partition the array. For example, we're given an array called in uppercase A, which has an lower beginning index of P and an ending index of R, A from P to R. We partition this original input array into two subarrays from P to Q-1 and then from Q+1 to R. So Q is the partition point, such that each element of the first partition is less than or equal to AQ. So Q is the pivot point, where everything prior to Q will be smaller than or equal to, but not greater than Q. Second step, we will conquer. So after divide the bigger problem, the bigger array, into smaller subarrays, subpartitions, we will sort the two subarrays from A, P to Q-1 and the second partition, Q+1 to R, by recursive calls to quicksort, to the original method. This is where the recursion comes into play. So that means we will divide the bigger problem into the smaller subproblems until the smaller subproblems is not divisible anymore. And then we're done. Eventually, we will combine, we will merge, just very similar to merge sort, since the subarrays are already sorted. That means we reach to a point when things are not divisible anymore. We can directly combine them so that the entire A array from P to R is now sorted. It's a little bit abstract to talk the theory like this. Now let's just take a look at the logic and the pseudocode behind quicksort. For example, we just name the quicksort the pseudocode. The method of this quicksort like this: A is the given array, P is the starting index, beginning index, R is the ending index. As long as P is smaller than R, which means there's at least one element within the range of this input array, then we'll call procedure called partition. This is the key to this entire quicksort. We'll partition A from P to R so that we return a pivot index, which is Q. And then we recursively call quicksort of the first partition, which is from P to Q-1, and then we'll recursively call quicksort for the second partition, which is Q+1 until R. So Q is the pivot index, right? You see Q is here, that is the pivot index between these two partitions. So for every partition that is prior to Q's index, that is, everything should be smaller than or equal to Q's value. And then for the second partition, everything behind Q's index up to the ending of the index should be greater than the Q's value. So the initial call to sort the entire array is going to be quicksort A from 1 until the length of the array. That's how we can sort the entire array. The key to this algorithm is the partition procedure, as I just said, which rearranges the subarray from P to R in place. Now let's take a look at its pseudocode and its logic. Partition A from P to R. So instead of naming it P and R, let's name it to start and end to make it more descriptive and meaningful. So I'll call these two parameters start and end. This is the code, or the pseudocode. How do we partition this? So first, we'll use the very last one as the pivot point, and then we'll create two more variables, I and j. I is going to help us keep track of the last element we can swap with. We'll start from start -1. We'll increment I before we do the swap. For j, it's going to start from the start index until the last element before the ending index. So that's why n -1. We compare the element pointed by j index. As long as the value pointed by j index is smaller than or equal to pivot, we'll increment I and we swap I and j. What's the purpose of doing this? This is helping us to move elements that are bigger than the current pivot back to the second partition. So we'll keep doing this from the start until the last element before the ending index. This is the for loop. And then after we have finished this for loop, we'll swap I+1 with end. The purpose of this line is to make sure that the pivot index, remember, end is the pivot index. So this last swap is to make sure that the pivot is going to be ending in the correct position after this partition. And then in the end, we'll return the new index of this pivot element, which is I+1. Okay, here's a diagram to show how this partition procedure divided the input array into 4 distinct regions. This lightly shaded part is the first partition that contains all values that are either smaller than or equal to this pivot. This P is standing for pivot, and this is the ending index, which is pointing at the pivot. This heavily shaded area is the second partition, where all values are exactly greater than the current pivot. And the unshaded partition is the one that hasn't been processed, that hasn't been put into one of the first 2 partitions yet. And the final one is the pivot that we choose. I hope this is helpful to help us understand. If it's not super clear yet, hang on just a few seconds. Let's just walk through one example, then we'll have a better idea of how this partition really works. First, for simplicity and easy to show all of the steps clearly in one slide, I'll simplify the variable names back to one character. So start will be P and end will be R. Now, suppose we're given this random array, 2871, 3564. And I is starting from the beginning index -1, if you recall from the pseudocode. P is the starting index, J will start from the starting index, and R is the ending index. How this is going to work is, in the beginning, none of the elements have been placed into either of the first 2 partitions. Now let's start the partition procedure on it. Second step, the element with value 2 is swapped with itself and put into the first partition of the smaller values, right? Because the pivot value is 4. 2 is actually smaller than 4. So 2 is going to be swapped with itself. So 2 is in the first partition now. Next step, we found 8. 8 is greater than 4. So we put 8 into the second partition. All right, then we'll continue. Continue to increment J. We found this 7 element. 7 element is still greater than 4. What we will do is that we put 7 into the second partition. We don't do anything, we just continue. Now we continue by incrementing J. So J becomes this. Now we found the element with value 1. 1 is actually smaller than 4. So 1 needs to be swapped with the last element pointed by I+1, which is 8. So that's why you see in the next step, we have swapped between 8 and 1. So 8 and 1, they are swapped. So that the lightly shaded area is still everything that is smaller than or equal to the pivot element. But everything in the heavily shaded area is everything that is greater than the pivot value, which is 4. All right, then we'll continue to increment J. J becomes to here, 5. 5 is greater than 4, so we should put 5 into the heavily shaded area. We continue to increment J. Now J is at 6. 6 is still greater than 4, so 6 should be put into the second partition, which is like this. Then the last step, what should we do? We should swap the pivot element, right? The pivot element with the very first element in the heavily shaded area to make sure that the pivot is in the correct position, which is like this. So now the pivot element is swapped as the last step. so that it lies in the correct position after this rearrangement, which is in the middle of the two partitions. At the end of this partition process, we have partitioned the values in the original array into 3 sets. Those that are less than or equal to the pivot, which is in the lightly shaded area, and a singleton set, which is this pivot, and the last or the third set, which is containing everything that is greater than the pivot. Now it returns the pivot's new index, which is I plus 1 here, right? Then we'll let this recursive call to continue for the first partition and for the second partition to continue to call this recursive function. So first you want to partition and then keep calling by itself until what? Until the beginning index is not smaller than the ending index. All right, you see now the output of this partition satisfies the specifications given for the divide step, which is everything in the first partition is smaller than or equal to the pivot index, and everything in the second partition is exactly greater than the pivot. That's the specification given by the divide step, if you recall, which is here. Partition the array into 2 subarrays, the first one p to q minus 1, and the second one q plus 1 to r, that each element of the first partition is less than or equal to aq, which is exactly looking like this, right? 2, 1, 3 are all smaller than or equal to 4, which is the pivot. Okay, now we will do partition again, but now the first partition of the previous call is namely the lightly shaded area is going to be like this. So here's the initial position of the pointers. I is always beginning minus 1, and then p is the beginning index, j will start from the beginning index, and r is 3, is pointing at 3. So we call this recursively, and then the second partition call is going to be starting like this, right? And then after we finish this, we'll call the same procedure for the second partition. So now we have 3 as the pivot. We'll check and swap. So first we found 2. 2 is smaller than the pivot, so it's going to be swapped with itself. And then we increment j. We found 1. 1 is still smaller than the pivot 3, so 1 will swap with itself also. Then we finished in this partition call, and then we return the new pivot index, which is 2. Which is here, which will let us call quicksort recursively again, but this time beginning and ending indices will be 0 and 1. So it will be like this. And then the first element and also the last element we need to check in this round is just 2. So 2 is not greater than the pivot, so we just need to break out the loop directly, and then we swap them before returning, which is going to looking like this. At this moment, partition index becomes 0, right? Partition index becomes 0. We return 0, which is the next round of the recursive call, which means it's not going to meet the specification of a new recursive call, which is what? Which is the beginning index needs to be exactly smaller than the ending index, meaning there's at least one element to be checked on. So the first part is sorted out, which is true, which is exactly the case. 1, 2, 3, 4, it's sorted out. The recursive call finished in the first part, and then it's going to continue on the second part. The second part is this heavily shaded area. I is going to be p minus 1. J is going to start from the beginning index, which is p, and ending index is r. So we'll call this part. The previous call we just finished is finished at here, this layer. And now the stack frame comes down to this quicksort, to this recursive call. Now it's sorting the second partition. So we'll just continue like this. We'll continue to call the partition and then sorting out everything. This is an 8-element sample array. For any size of the array, quicksort will continue to recursively call itself by calling the partition and then eventually sorting everything out by doing the swap. So what's the time complexity of this partition? The time complexity is going to be O(n). To be more precise, this n equals to r minus p plus 1. This is exactly how many times that we need to do the check and swap. Now let's put this idea into real code and see how it works and how everything will make sense. All right, I have created this class for quicksort, and then this is the input. This is the method signature. How can we implement quicksort? It's going to be very similar to pseudocode as long as we have the correct syntax in place. So it's very straightforward. First, I'll create a quicksort First, I'll create a quicksort method, which is going to take in 3 parameters, right? First is the array itself, and then we need a beginning and ending index. So the beginning is going to be 0. Ending index, if you recall, to sort this entire array is going to be array's real length, which is going to be -1. So this is the entry point of this entire quicksort if we want to sort this entire array. And then in the end, we'll just return quick array. Create method quicksort, yes, array. And this one, I'll call it begin. And this is the ending index. If you recall from our slides, from the pseudocode, the first step we want to check is if p is smaller than r, which is if begin index is smaller than ending index. This is the condition for this recursive call. What this means is if beginning index is equal to end or greater than end, that means there's nothing within this range. There's no single element within this range that we need to sort out. Then we can just break out. We're finished, right? All right. Next step is we want to do the partition. So the value that's going to be returned is the partition index. And now we need to implement this partition method, which is array begin index and ending index. Here is the partition method. We'll put the main logic in place first, and then we'll implement the partition method. After we find this partition index, what we'll do, we'll recursively call this quicksort to recursively sort both the first partition and the second partition divided by this partition index. So we'll call quicksort array begin, and the ending index is partition index -1. Right? And then we'll copy this and just modify this partition index +1. Next part is the ending index. This is the entire main logic of quicksort. Now it comes to the meat, the juicy part of this entire quicksort, which is this partition procedure. How can we implement this partition procedure? Very similar to exactly what we just saw, the pseudocode, the real logic. Let's create a method. Partition array begin and end. All right. The first step, we pick the last element as the pivot. All right. I'll call it pivot array end. This is the ending index, which we will use as the pivot. And then we'll use 2 new variables called I and j. I will start from begin -1. And then we'll have another variable called j. This j will use the for loop to continue to check from the beginning index until the last element. From the beginning index until the last element before the ending index, which is n-1. We'll keep increment j along this way. What we will do is that we will check if this element pointed by index j is smaller than or equal to pivot, right? If that is the case, first we'll increment I. Next step, we will swap. We will swap this I and j to make sure that the first partition, everything in the first partition is exactly smaller than or equal to pivot, right? This is the purpose of doing this. All right, this swap I'm going to implement in just a second. In Java, it doesn't have a built-in swap method. After this for loop, right, we have finished traversing, we have finished checking this entire array from beginning index until the last element before the ending index. What we need to do, we need to put pivot into the correct position, which is I+1 and ending index, which is pointing at the pivot. We need to put the pivot into the correct position, which should be I+1. And then in the end, we're going to return I+1, which is the pivot index, the new index for the pivot. Now let's implement this. Oops, what did I do? I need to create a method, I and j, very simple, temp array I. Now we can safely override this with j. Next is j and assign temp back to j. All right, this is the entire quicksort algorithm, how it can be implemented in Java. Now let's just quickly run this to see there is no compilation error. So let's run this. It should work. It's not really working. What did I miss? All right, this is one. it should be exactly smaller than n, which means it's going to reach the last element before n instead of hitting n. If I still decrement it by 1, it's going to give us the wrong answer. Alright, now it looks correct to me. Now let me quickly run this again. Run. Alright, now it's correct. We have 2 3s, so the correct final after sorting is 1, 2, 3, 3, 5, 6, 7, 5, 6, 7, 8. Alright, that's correct. Cool. This is how we can implement this quicksort in real Java code. I'll publish this into my GitHub repo, and I'll put the link to this GitHub repo down in the description box below. So feel free to check it out and play around with this to see how this can be implemented using real Java code for the famous partition sorting algorithm. I highly encourage you to do so. It's going to give you more hands-on experiences to see how it really works in real Java code. Now coming back to the slides, let's talk about the complexity of quicksort. The best case is going to be nlogn. So that's why it's very efficient in a lot of cases. It's actually beating merge sort and heap sort in a lot of cases. And that's why it's so preferred than other sorting algorithms. But in the worst case, it's going to be n squared, which is very bad. But this is a very rare case that rarely happens in real world. And its average case is actually very close to its best case, which is nlogn. The detailed mathematical analysis is beyond the scope of this one. I'll probably make another video to talk about why the time complexity is looking like this. Now I'd like to address one question we briefly talked about in the beginning of the video, which is why the space complexity. I said it's in-place sorting, but why it's not O1, instead it's O-log-n? Well, the reason for that, the extra space is the O-log-n stack frames due to the recursion nature of how quicksort is usually implemented. Of course, you could argue that you could implement quicksort iteratively, for example, using a loop instead of recursion. Then you would still need to maintain an auxiliary stack because quicksort has 2 recursive calls and not just one. Right? So we partition first into 2 partitions, and then we recursively call quicksort on the first and the second partitions. Finally, this O-log-n, this O-log-n, although it's not 1, but it's pretty much equivalent to 1. Because for pretty much all practical applications, this O-log-n is very, very small. That is almost equivalent to constant. So every constant factor, like the overhead of your data structure, will have a greater impact on memory. For example, even if you have an array of the maximum size allowed by Java, which is 2 to the power of 31, that number of elements, which is about 8 gigabytes, quicksort would only require what? Would only require 31 stack frames. So the ballpark about that is maybe 100 bytes per frame. So a total, maybe 3 kilobytes total. So 3 kilobytes versus 8 gigabytes, which is nothing, right? Compared with the memory for the actual array. So in reality, almost anything that is something similar to log-n is pretty much the same as constant. That's what we mean in actual. It's basically in-place sorting. All right, that's the end of this video. I hope this video does help people better understand quicksort. If that's the case, please do me a favor and hit the like button. That's going to help a lot with the YouTube algorithm. And don't forget to subscribe to my channel. Videos like this takes me a lot of time and effort to prepare and make. If you don't mind, please share this video with your classmates, colleagues, friends, and leave me any comments down below. I would really appreciate it. And I have accumulated quite a lot of other CS lectures or algorithms or data structures or other LeetCode problems. So feel free to check out my other videos or my other playlists. Hopefully I'll see you guys in just a few short seconds. Thanks very much.